Let's do the second question here, right? So we've already got what's the greatest height it will rise to above the surface, right? What is the speed when it's gone 50 kilometers straight up from the surface of the moon, right? So it's fired at 560 meters per second. So let's figure out what speed it's going when it's gone 50 kilometers straight up. Now, the first thing we got to do is we got to figure out it's going to start at the surface of the moon, right? And the radius of the moon is 1.737 times 10 to the 6th meters. And the mass of the moon is 7.35 times 10 to the 22nd kilograms, right? But this thing is going to go up 50 kilometers above the surface of the moon. So let's figure out what that new radius is. So my new radius is the radius of the moon, 1.737 times 10 to the 6th plus 50 times 10 to the 3rd. So let's figure that out. That's the first thing. So 1.737 E6 plus 50 E3 is 1.787 times 10 to the 6th meters. So that's the new radius, okay? So now what we're going to do is we've got this bullet. Here we are on the moon, right? Not to scale. And we fire it up, and at first it's going, what, 560? But when it's here, when it's 50 kilometers above the surface, what's its velocity now, right? Here it's going 560. What's the new velocity, okay? So I'm going to say what kinetic plus potential here is kinetic plus potential there, okay? Let's do that. So it's going to be minus g, mass of the moon, mass of the bullet, over r, which is the radius of the moon, right? Plus 1/2 little mass, right, times 560, right? That velocity squared. That's going to equal, at the new elevation, minus g, mass of the moon, mass of the bullet, over r, plus 1/2. And we're solving for this new velocity, right? I'll call it v prime, whatever that is, right? Okay. Now notice that the mass of the bullet actually cancels from all of these. This makes sense because if the bullet had, say, more mass, it would have more kinetic energy, but it would require more energy, but in the same proportion, to remove it from the surface of the moon. Okay, so let's see. Let's plug in numbers. So minus g times 7.35 E22 over 1.737 E6 plus 1/2 560 squared equals, let's see, minus g times 7.35 E22 divided by, this is my new radius, right? So now I'm 1.787 times 10 to the 6th plus 1/2 v squared. And this is what we're solving for, is that v squared. So what I'm going to do is I'm going to figure out this whole side here, and then I'm going to subtract this negative term. So basically make that positive and add it. Okay, so let's find this whole side here. So alpha F1 opposite of g times 7.35. I stored the number 6.67 times 10 to the minus 11th in the letter g on my calculator. That's how clever I am. Okay, E22, and then r is 1.737 E6 plus 0.5 times 560 squared. Oh, whoops. That was a failure. All right, so let's see. Plus 0.5 times 560 squared. I put that in the denominator. Okay, so the whole left side here is solidly below water here. In other words, this term's negative, which means that we're still gravitationally bound, right? 26655. I love this number, 66.149. Okay, equals, and then this number here is alpha F1, opposite of G, times 7.35, E22, and then my new number is the 1.787 E6. So this guy is negative 2743396.754. All right, so now I'm going to do this left side, that guy, minus the right side. And I get that, it's good news that I get a positive number here. Let's see, 77830.605 is 1/2 v squared. Okay, so multiply by 2. Take the square root of that number. 394. Oh, 394.53. So actually 395 is what I got. 4.53. So I'd have to say 395 meters per second, I think. Wow, right. I'll have to edit that. There,